It's a great pleasure to be here. I just was looking in my email to this morning. I was searching. I realized that the first correspondence I had with Wojtek was in 2002 when he sent me an email. I had just accepted to join the group in Maryland as a postdoc, and he invited me to the first FFT, which was in 2002. And I found the program of that, and then I've been, of course, I've been to FFT several times after that, and it's a great pleasure to be here. Thank you for the invitation. Today I'm going to talk about some new work we did. This is joint work with Babru Joshi, Xiaowei Li, and Yaniv Plan, all at UBC. And Babru is a postdoc, and Xiaowei is a graduate student about to finish, and Yaniv is my colleague. So the problem that we look at is generally solving an inverse problem, and the idea will be, as it's clear in the title, using a generative model as our signal model. Let me just try to go a little bit over this and try to define the problem and say a few things about the background. So we have observations of a signal X that are contaminated by some noise. Here, X star is our signal or source of data. The A is the forward operator, and this is additive noise. I will stick to this model. My goal is to estimate recover X star from Y. And clearly, this is not an easy problem in general, because often the forward operator is ill-posed, and also we have to find a tractable method to do this inversion. To be able to do that, we need to restrict our search space, so to say. So we need to model the signals of interest, right? So let's say signal class. So we can restrict our search to the signal class, or we can regularize. Okay, some examples, there are many examples of, obviously, but some examples that I will touch on during this talk are denoising and compressed sensing. And quantization combined with these problems. And again, there are many other examples that I'm not going to talk about today, but the methods that I will describe can and do apply to those methods as well, like imaging, inpainting, and so on. Okay, so obviously here the question is, how do we model the signals? And so let's just be a little bit going back. I'm going to call the first approach the deterministic approach, or you could say the function space approach, or there are many different ways to denote this. The main point is here, you assume that your signal is in a fixed signal class, which is a subset of a high dimensional ambient space. Okay, it could be, for example, this could be a k-dimensional subspace of Rn, or it could be a more complicated set, some convex set. But the point is, you fix the set, you know that set is a good model, and then you solve your inverse problem basically by solving this generic program, which will give you an approximation by minimizing the error that you get with the constraint that your solution is in this predetermined signal model. Okay, so this gives you a constraint optimization problem. You can, of course, turn this to an unconstrained one using the usual Lagrange approach. And there are many signals of interest in the literature that people have considered. It's not the right color. So, okay, some examples here. I don't want to spend too much time, but I want to just, for example, band-limited functions as a subset of L2. That's of interest in sampling theory, analog to digital conversion. You can have sparse signals or signals with sparse transforms. Let's call this maybe J-sparse signals in Rn. Okay, so or you can have signals sparse with respect to a dictionary, and you can also have learned models here. So even though I'm calling this the deterministic approach, you can still do some learning, but you learn the model, you fix the model as a set, and then you're done with that. For example, you can take the data set, you can find the Cartan and the web basis, you fix the K dominant directions, and then you use that subspace as your signal model. So once you fix it, then you have a fixed set. Okay, so just to be a bit precise, or let me just also write a few forward maps that we will use. This would correspond to denoising, and you could have your forward map to be an m by n matrix, let's say, with m much less than n. This could fit into the compressed sensing framework that I mentioned. Or you could incorporate quantization into this measurement. So you could have a Q phi, where Q is a quantizer. Okay, it's a map that takes values in the continuum and maps them to a finite set. Okay, so this is the deterministic approach. I will come back to this, but the second approach that actually will motivate what we will do is the Bayesian framework. Okay, so in the Bayesian framework, our observation model is the same. And the difference is the way we model the signal. This time we're going to think of X star as a realization of a random vector, okay, of a random vector X. This is, let's say, in Rn, okay? N is going to be my ambient dimension. All right, so then Px is the density of, or the distribution of X, and this is what captures our information. Instead of fixing a set, now we have a distribution. Our information about the signal class. Okay, and then of course, when you do this, your measurement you can write as a random variable or random vector as well. And when you're given your measurements and you want to estimate X, what you are really interested in is the posterior distribution. And you want to maximize this. So this is the so-called map estimator. Okay, so this is the trick I have now. So my last page is now on the left. All right, so I want to maximize this posterior distribution, and it is kind of easy to see that that is the same thing as doing using Bayes rule, minimizing negative log of the likelihood, and then here the prior. Okay, so this guy depends on the noise, and if the noise is Gaussian, and if the noise is Gaussian, it's going to be basically the 2 norm squared of the mismatch. And this guy here, I'm going to call R of X, that's the regularization term. And R of X depends directly on the prior. Okay, so this is how we want to incorporate the prior into the solution of this inverse problem. Okay, so what we need the prior distribution. What we can do is we can make assumptions based on observations on data distribution. Option 1, make assumptions. For example, you can say that I don't know, there's a transform, Weber transform of your signals. The coefficients are IID Laplacian, something like this. And this would give you the R of X would be lambda times the 1 norm of the coefficients. Okay, it leads to unconstrained cluster. And this is a way of combining the two approaches. You can find also a function space that gives you this an unconstrained version of a constraint optimization problem with the appropriate function space there. But anyway, so this is one option. And finally, option 2 is actually learning the prior, use the learned prior. And specifically, we're gonna, I mean, there are different ways of doing this. I will in the rest of this talk, I will be looking at these in the form of a deep generative model. Okay, these can be trained using different techniques, variation autoencoders or generative adversarial networks. I will not be interested in that part of it. I will believe that whatever network I was given has been trained in a way that I will describe now. So my goal is, once you have a trained network, how do you use that to solve inverse problems? Okay. All right, so some related literature about this. Let me also make the disclaimer, I'm not able, and also I don't intend to give a full literature review in this general area. There's a lot of works that have looked at this problem. I will only mention here some related literature that will be consequential to what I will do. So one of them is the compressed sensing with generative models paper. This is probably one of the most important papers in this direction, as far as I'm concerned. This is by Bora, Jalal, Eric Price, and Demarques. And it is in about 2017, I think. And then there's this is a paper where the framework of generative models has been used to solve compressed sensing problems. And then there's work by Paul Hand and his collaborators, various collaborators, that look at a particular algorithm to solve these related inverse problems, and that give a proof of convergence for this algorithm. So these are basically what follows. Rest is I'm going to describe how we will set up the problem, and then I'll show that we have an alternative algorithm that has some advantages to again provably invert these generative networks and thus be applied to inverse problems. Okay, so let me now talk a little bit about the specific approach that was taken, especially by Paul Hunt, but also in other papers. So first of all, the generator network. Any questions, by the way? Maybe this is a good point to. Okay, I'm going to then define a little bit more clearly what I mean by a generator network. Okay, so this is a map G. It's going to be from Rk to Rm, and here K is much smaller than M. And G maps Z, which is a standard Gaussian vector, okay, in Rk, obviously, to a random variable x, which is G of Z. And this is a random vector in Rm. This is our prior. So the distribution of this is our prior distribution that we want to use. And this is called the latent code. So this is a way of generating the prior or sampling the prior. If you want to sample from the prior distribution, you generate a Gaussian vector and then apply the map G to it. So that creates a sample from the prior. Okay. Okay, so great. We have this black box that applies G. Now, how do we use that to set up an optimization problem to solve our inverse problem? Okay, so remember the regularization term was negative log px. So we just want to have a very coarse approximation of this. And we're going to say, you know what? My regularization term is infinite if x is not in the range of G. This is the range. And 0 if x is in the range of G. So I'm just restricting myself to the range of G, which connects us in some way back to our deterministic framework. So this is the connection between the two. Once you've trained G and you fix your G, when you formulate the problem like this, you are going back to the deterministic framework where you can solve a constraint optimization problem. So my approximation then could be written as arg min of ax minus y to norm squared, but I want to pick my x from the range of G. Okay. Alternatively, you could say I want to find this time over Z of a G of Z minus y to norm, and then x tilde would be just G of Z tilde. Okay. So this is the algorithm. We put a star here, which I will come back to this. Okay, so this is what I want to solve. Now, what do? I want to restrict my map a little bit more. Our map is going to be a generative neural net. So that would be something that is growing like this. Forgive my drawing. So this is the width of this is M0, the width of this is M1, and the depth of the network is D. So this is MD. There's a map W1 here. There's a map W2, and so on. WD. These are matrices, and there's an activation function sigma acting on each layer. Okay, so you feed in Z, and you get that X. And if you write this the way I wrote it here, kind of G of Z is going to be sigma of WD, sigma of WD minus 1, and so on, sigma of W1 Z. Okay, where my Wi are matrices, and I by n minus 1, and sigma is value. Okay, sigma x is x if x bigger than 0 and 0 otherwise. I will later make some comments about relaxing this, but for now, let's just write it like that. And the goal is now solving. Goal. So start with this G. Okay, star is here. This is star. Of course, this is star. Okay. So I've kind of restricted myself quite a bit. Also, let me just say one more thing. Let me add to this problem something about this A. Here I have the forward operator A. Let's say my forward operator is a matrix phi, which is M by ND. Okay, here ND is the big dimension and M is much smaller than MD. This is going to be, I can think of this as the compressed sensing matrix. Okay, it could also be identity if I'm looking at the noise. Now, there's an algorithm for solving this that I mentioned before that comes with a proof of convergence. This is by Huang, Hand, Heckel, and Vorominsky. And the algorithm is gradient based. And what they do is they look at these gradient based updates. So k plus 1 is that k minus some step size, and then I'm gonna define what these are. D1 W1 transpose goes like this, DD WD transpose, and phi transpose, that's the measurement matrix, and then I have the measurement phi of G of z k minus 1. Okay, so this is their algorithm, and the idea here, these are matrices basically with ones or zeros in the diagonal, and they select active rows of Wj. The active rows of Wj means if you look at, for example, this guy here, just look at this one, W1 times Z, each row, you compute the inner product of each row with Z, and sigma acts on this vector entry-wise. So if that inner product is positive, then it stays. If it's negative, it's 0. So what this does is basically it replaces those rows whose inner product with Z is negative with 0. So these are, let me just say this, select active rows of W1 and Wj, okay, in each, and they are dependent on the iterate. Okay, so at each iteration you have to change dj, and then when you do this, you can observe that at points that the cost function is differentiable. This is doing exactly gradient descent, and that's great. And what happens is, with this adaptive update in each step of these DJs, you get to prove, this is again the work by Wang et al., that they prove that if there are some conditions, Wj are IID Gaussian, so there is the assumption of the weights being random of the network. Okay, this is a big assumption, but it seems to be an okay assumption under certain circumstances, and it's done in the literature very commonly. And so this is one assumption they make. The other assumption they make is phi needs to be appropriate. Just like in the compressed sensing literature, it has to satisfy a property like RIP on the range of on the difference of range of G, Minkowski difference of range of G itself, and then M needs to be sufficiently large, sufficient number of measurements, and if these things hold, and again sigma is ReLU, the activation is ReLU. If all these things hold, then they show that ZK, so ZK converges to Z star, and thus G of ZK converges to G of Z star. Okay, with high probability. All right. So this is great. It is an algorithm with a convergence guarantee. There are restrictions, limitations, that some of which are hard to avoid, some of which maybe are potentially doable. For example, let me say a few of the limitations that I will later on tell you that we can avoid, at least in the case of our contributed algorithm. One is that sigma has to be ReLU. Here we can maybe potentially relax that a bit. The weight matrices are IID Gaussian. Here we potentially can relax that a bit. There's no bias in the activation function. We might be able to add bias and still hope that we get something that converges. Okay, so these are issues we want to look, but also the simplicity of the problem. So of the algorithm, the way here at each iteration you have to compute these DJs, and so we said, what if we drop those DJs? What happens? So let's get something. I'm gonna say our contribution. What we call plugin. There's a way of saying partially linearized updates, something. We came up with with this name in a brainstorming session. Okay, what is the thing we drop DJ? And thus the algorithm reduces to this. W1 transpose, W2 transpose, WD transpose, phi transpose. Okay, then we have the rest is the same, phi G of ZK minus Y. Okay, so this is the plugin algorithm. at least in the case of compressed sensing. If the operator is, the forward operator is different, identity is the same. You can have phi equals identity. For different forward operators, you might have to do other things. But for now, let's just consider this. And I'm going to come back to why we believe that we thought that dropping DJs would be okay. But let me first state the assumptions that we need to make and the theorem that we can prove, and then we'll talk about that. Okay, so the assumptions, these are the assumptions we have in our original paper, which is published in this year's NeurIPS proceedings. So A0, as I said, I will relax some of them towards the end of the talk. Our sigma is value. Our Wi are each ni by ni minus 1. IID, each column, about each entry is IID non 0, 1, normal 0, 1 over ni. Okay, and then the next assumption is this ni, there is an expansivity requirement, some constant times 5 to the ni, 5 to the I. Sorry, I'm writing this because I want to say something about the sum log terms. And I'll come back to this. Let me finish writing all these things. Phi is in m by nd, as I said. And again, IID Gaussian with IID Gaussian entries. And m has to be sufficiently big, which is some constant times 0. That constant depends on the times sum log terms again. And finally, we need the noise not to depend on the matrices. So depend on phi or WJ. Okay, so these are our conditions, and under these conditions we can prove the following. This is by Babru, Shaway, Yaniv, and myself. We can say, suppose let's denote the initialization is Z0, and let's say Z0 minus Z star is less than some R. By the way, no limit on R. R can be anything. It just denotes what the original distance is, where we started. And let's set the step size to 2 to the D. We can have it less than that, but this is the good one to prove things. So then we can prove that K minus Z star is 2 to the minus K times R plus noise. Okay, that's the noise level. Okay, and this gives us in the signal space the reconstruction error is again we just make the restrict the Lipschitz constant of the whole map to 3 with high probability. You can make it smaller than that too, but that is so this is 3 times whatever I had up there, 2 to the minus KR plus 3C eta, and this holds with probability greater than or equal to 1 minus something K plus 4 to the negative 10 and that. Okay, so this is our main result. Okay, now my next job will be talking about the theorem again. I'm happy to answer any questions if there are. Okay. Let me make a few remarks, as I said, that I think are interesting and important. The first one is, if you look at the layer width constraint that's given by the assumption A2 here, that constraint allows for contractive layers. There's of course, overall expansivity requirement, but the lower bound on each ni is in terms of n naught, not in terms of ni minus 1. So we can have contractive layers as long as we have the overall expansivity condition satisfied. The first layer has to be expansive, obviously, but after that, so I want to make this remark here. Assumption. This was one issue in the literature, that all the results were for networks that had to be strictly expansive. So in our result actually goes around that. Allows for contractive layers. Okay. The second one is convergence is geometric from the get-go. From the beginning. Whereas the gradient descent method converges geometrically after it gets to a neighborhood of the solution, and until that, there's an upper bound on how many iterations that will take, but the convergence at that level is not geometric. You start out there, you kind of get to the neighborhood, then you converge geometrically. Okay, so the third important remark here is there's no restriction on how big the noise term can be. Okay. Okay, so I'm now checking the time. I'm going to tell a little bit about the motivation. I had promised that I'll tell you why we thought we could drop the D's. Let me do that, and then say a few things about the extensions that we recently made, and maybe show you a few numerical experiments.
By the way, Ozgur, you have a question from Suleiman about whether A0 is essential or not.
Okay. A0 is essential or not. A0 is sigma Israeli. So what I can, first of all, you can relax it immediately to any positively homogeneous function. So leaky value, for example, is fine. If you want to relax it further, that becomes tricky in different ways. There's a subspace counting argument that in the proof that that needs to be modified. That can be potentially done, but there is an algorithmic problem with normalization. Let me state the lemma that I use to motivate, and then let me give a little bit more of an answer to this question. Thank you, Suleiman. That's a nice question, and I'll come back to it. So let me, as I said, I'm going to say proof sketch. I don't know how much I will sketch really the rest of the proof, but let me look at this case. D equals 1 layer, no compressed sensing matrix, phi is identity, and no noise. Okay, so in this case, my Y is sigma of W1 X star. Sorry, W1 Z star, right? That's G of Z star. And we want to find Z star. Okay. And our claim here, and again, this is the motivation, is the first iteration of plugin. If you take the expected value, you get the solution. In other words, it is first iteration of plugin is an unbiased estimator. Unbiased estimator. And the proof of this depends on the following lemma. This is by, I know this from Yaniv and Roman Version's work, but also I believe it was observed by Brillinger in an earlier paper. And the lemma is the following. If you look at the function that is positively homogeneous, and say A is an n by n matrix, and that is IID with Gaussian entries, then the expected value of A transpose sigma AX is lambda times X, where lambda is expected value of G times sigma G. Okay, where G is standard Gaussian. And in particular, if sigma is real U, then lambda is a half. Okay, and this is basically behind the step size that we have here in the thing. I should have said somewhere, actually. You know what? I'm gonna go to the page here. Let me put directly the step size as 2 to the D. Different colors so you can see the change that I did. Okay, that's better. And that 2 to the D comes from this lambda equals a half here. And the way it comes is now if you write Z1, which is Z0 minus minus 2 times W1 transpose sigma of W1. So let's just go here, W1 Z star. Minus, so what am I doing? Sorry. Okay. So the algorithm here, take the current iterate, which is Z0, and you subtract from that the actual measurement, which is this. Okay. So if you take the expectation of both sides, you have an expected value here, expected value of, let me just write it like this. Okay, so what do you get? You get expected value of Z0 is Z0, and then you get 2 times the expected value of this entity here, which is a half Z0 by the lemma, and then plus 2 times a half W1 Z W1 transpose sigma W1 Z star, that is the expected value Z star. Okay, so this is just the lemma applied to the first iteration, and as you can see, these cancel, and you get Z star. Okay, so this is the motivation, at least why we thought it might work, and it did work, and then we proved that it did work. The proof, of course, is much more further iterates are not. Unbiased estimators, and so you need to do use generic chaining, basically, of mixed tail. Mixed tail processes, and then you also need to do some counting, where to go to D layer, you need to count you need to cover the range of G with unions of subspaces, and for that so in fact you be a little bit more specific. If you call GI as the first I layers of the network, is that then we need to show that the range of GI is a subset of Ni and union of Ni and zero-dimensional subspaces. And then what Ni is turns out to be, it can be bounded by the product of this. Something like that. That's considered here, and so on. Okay, so there's definitely no time to go through the details of this, but going back to the question, this counting needs to be done, and I need to have this type of an unbiased estimator situation. Okay, so if you look at this lemma, you can replace this sigma with other functions, but then the normalization will depend on x. That will bring us an xk or zk dependent normalization factor into the iteration. So if you look at the iteration of let me just go back here one page. Okay, here, this is really clean and nice. And if you do change sigma to some other function that is not positively homogeneous, there's a normalization issue we need to deal with. We might be able to deal with it. I'm not saying it's not possible, but there's no clear answer that I can give to you right now. Okay, I have very little time left. I just want to say a few things and then show very quickly a few examples. Some extensions, these are very recent and exciting. The first one is we can actually have a projected version of plugin where we use the fact we basically think about what G is supposed to be doing. G is supposed to be taking a random variable that is each entry is standard normal and mapping it to G of Z. So just restricting to the range of G is maybe not the best. We can do a little bit more because we know that when we have an X star, there should be, given X star, there should be some Z star close to kind of with K. K is the dimension of the original space. So we shouldn't be looking at it in the general range, but we should try to go back to a ball of roughly reduce this. So we can modify plugin to incorporate something like that. And we can assume that our Z star is in a ball with radius Z, and maybe let me call it R tilde, and that R tilde should capture this root K close to be that. And K is n0 actually here. Let me just like that. Sorry, I want to say this, and if you do this, if you then assume this that Z star is in this convex set, then you can modify Zk. You can replace Zk in plugin after you compute Zk plus 1 as before. You replace it with the projection of it. Okay, and we can prove that this converges. The proof is easy to modify to show that, and I'll show you in the experiments that actually this performs quite better than the original. And in fact, this idea can be applied to gradient descent as well. I don't have a proof for that, but it seems that numerically it works really nicely. The second recent, we can add bias. Okay, we can handle bias now. And 3, the weight matrices, we can relax the Gaussianity to symmetric, isotropic, sub-Gaussian matrices that will work. And 4, we can work with sub-Gaussian compressed tensor matrices. And 5, we can actually also kind of do quantization here. And I'll show you a couple experiments now with that. I hope I have a few minutes. I'm really not going to spend too much time. I just want to show that these things that I'm talking about kind of work in experiments. So if it's okay, I'll stop sharing this, and I'm going to share this instead. Okay, so these are some numerical experiments, and what you on the left you see the latent code recovery, and on the right you see the signal recovery. And
sorry,
I'm not sure we can see this. There is a maybe there is a blocking window in front that you're not showing.
It says screen sharing is paused. Why would it do that?
Not sure why, but
okay, I'm gonna stop it again. Let me try one more time. Do you see it now?
Now it's okay.
That's much better.
Okay, perfect. So I was saying on the left we see the recovery of the latent code vector, and on the right we see the recovery in the signal space. And the horizontal axis is the relative noise level, and the vertical axis is the reconstruction error, again relative. So this is an example where we do denoising, and they're all denoising when noise level is small, and you can see that the plugin and gradient plugin and projected plugin. By the way, the purple one is the projected version of the algorithm. They are not doing as well as gradient descent, but they are doing reasonably well, especially in the signal space. Now, let me show you another example where we are looking at a let's say lower sampling rate example, where the latent code dimension is 70. In the other one it was 20, and again all these things work. The projected ones work better. And furthermore, I want to emphasize that in the latent code space, the errors are much bigger than they are in the signal space. So this tells me that there's some non-uniqueness issues that we have. It's kind of like finding a sparsity representation with respect to a redundant dictionary. So even though the code vector is not necessarily being recovered fully, the image is being recovered. Early stopping helps, just to throw in there. Let me also say that these are compressed sensing experiments. They seem to be working fine. Again, this is the noise level versus reconstruction error. They're close to each other, as you can see. In fact, there's somewhat of denoising going on together with compressive sensing here, because with the 0.25 relative noise level, we are getting something on the order of a little bit less than 0.25 relative reconstruction error. This is another one where the original plugin doesn't work as well, but the projected one does work really well, and together with gradient descent. And finally, let me show you, this is a trained network, so it doesn't satisfy any of the assumptions necessarily that we make about random weights and stuff like that. Still, all these algorithms seem to be performing okay, and the reconstructions that we get from these compressed sensing measurements of these images are pretty cool. So the left corner, this one is the original image, and this is what plugin recovers. This is what projected plugin recovers. Remember, we are doing compressed sensing, and we are doing adding noise on top of the measurements and doing compressed sensing with that. 1-bit quantization, it is behaving as it should, and this is kind of also cool. And I want to finish with this. Here, what we're doing is we are using a high multi-bit quantizer, and we are incorporating that information into the plugin. So we are incorporating that into the plugin iterations, and that improves the reconstruction tremendously. The blue is the regular plugin where we kind of ignore, because this is the high accuracy quantization. You can say, okay, I'm just going to assume those are my measurements, and then assume that whatever I'm missing is noise. And if you do that, you get the blue, and then if you do that with the gradient descent, you get red. But because of the nice structure of plugin, you can actually adjust plugin and get this, incorporate this quantizer into your iterations. And when you do that, you get the black one here, which is an order of magnitude better in terms of relative reconstruction error. Okay, I'll stop there. Thank you so much.